right, so the 2001 calculus exam had a problem, number 4, in which all 4 parts are solvable with just an understanding of derivatives. So let's jump in and see how we do. For part 8, it says find all x values where the graph of h has a horizontal tangent, and then determine whether h has a local max, local min, or neither at each of these values. So let's start with what a horizontal tangent is and what it can be. So we know we can have horizontal tangents in a number of places. In this example, we have a horizontal tangent at a max. We could also have horizontal tangent lines at a min. But we could also, in a third scenario, have neither a max or a min. So hence they're saying find where you have the horizontal tangent and then identify that as a max, min, or neither. We have 3 options here. So let's look at some notes and see what we need for each. In the case of a relative maximum, I'm looking on the left, not only do you need to check the box of having a horizontal tangent line, but also your derivative should change from being positive to then being negative. That indicates that your graph was increasing and then decreasing. So f prime has to also change from positive to negative in order to have a relative max. So if those 2 boxes are checked, we've got a max. Now, in the case of a min, you also need baseline to have a horizontal tangent line, of course, but then your slope should be changing from negative on the left to positive on the right. If those 2 boxes are checked, then we definitely have a relative min. So we have a plateau, and specifically our graph is changing from decreasing to increasing. Now notice in this third scenario over here, my graph has a horizontal tangent line, but it's increasing on the left, and it continues increasing on the right. So the slope doesn't change signs. The slope is positive and it levels out, then it remains positive after that. So at the very least, in order to have a relative extrema, meaning a max or a min, you need to have 2 things. You need a horizontal tangent, and f prime of x, the derivative, should switch signs. So we're looking for all the x values where we have a horizontal tangent. So we know for a horizontal tangent, we need to set the derivative equal to 0. They've already given me the derivative, so I can just start by setting that equal to 0. So I know that if I have a fraction and I need the entire fraction to equal 0, the only thing that really matters is that the numerator is 0, because 0 divided by anything is 0. So I only need to work with the numerator here. Seeing a minus sign in between, I'll solve for this by factoring difference of squares, leaving me with x equals positive radical 2 and x equals negative radical 2. Now there's another way you could have finished that part of that problem, which is to move the 2 to the other side and then take square roots, but you'd have to remember the plus or minus there in order to get the points. And 80% of students forget to do that, so I'm going to highly recommend and model from now on the difference of squares approach. So we know that these are the 2 values where we have a horizontal tangent, but we now need to classify them. So we need to figure out what's happening around them, whether the graphs are increasing or decreasing. We'll use a number line to analyze further. So we're going to stick negative radical 2 and positive radical 2 are zeros. But keep in mind, we're interested in how the entire graph is behaving, so we need to look back at our original function and grab the roots not only from the numerator, which were x equals plus and minus radical 2, but also the roots from the denominator, and you can see our denominator is giving us a root at 0. Now, we know that the derivative is undefined at 0, but still our graph will behave uniquely around these values. So since it's positive on the left, we're going to start here positive. And at positive radical 2, the factor above it has an exponent of 1, so we'll flip. At x equals 0, we have an exponent of 1 as well, so we'll flip. And then at negative radical 2, we have the same situation. So what's this tell us about the graph? Well, on the left of negative radical 2, we have a negative slope. Our derivative is negative, so my graph is decreasing. Between root 2 and radical 2, h prime is positive, so h is increasing. H prime is negative, so if the slope is negative, then the graph is decreasing, and then again, we are positive slopes beyond radical 2. So that's telling me clearly that I have a relative min here, and I have a relative min here as well. So our conclusion is h of x has relative minima at x equals plus and minus radical 2. And our reasoning is, since h prime of x switches from negative to positive, so our slopes change from negative to positive, showing me that I have a relative min. Part B says, on what intervals, if any, is the graph of h concave up? So first thing to note is, anytime we're dealing with concavity, we need to use the second derivative. So let's jump right in. I'll find the second derivative of h, meaning I need to take the derivative once on the right here, and that's as easy as using the quotient rule. So let's do our quotient rule. Low d high minus high, and derivative of the bottom is just 1, d low, all over low squared. Let's clean that up a little bit. 2x squared minus x squared, distributing the negative, that gives me a plus 2 all over x squared, and then combining our like terms, I have 2x squared minus 1x squared, leaves me with just x squared plus 2 over x squared. Great. We have our second derivative, but the question asks for where we concave up. So you need to know that h will be concave up where h double prime is greater than 0. That's what it means to be concave up. Similarly, if I wanted concave down, I would be looking for where the second derivative is less than 0. So it's very intuitive. If the second derivative is positive, it's concave up. If it's negative, it's concave down. Well, we need to see where it's positive, and in order to figure that out, we will use a number line. So number lines will always tell us the positive and negative regions. Since we're dealing with the second derivative, let's label our number line. And as before, we need the roots from the numerator and the denominator. So let me put a skull here, commonly forgotten. We need to get roots. From the numerator and the denominator. So checking out the top, notice we have a sum of squares, so we have no roots from the top. Our denominator yields a root of 0, so that's the only thing that will go on our number line. So let's start on the right side, is positive out in front, so I'll put a plus sign, and at 0, notice that the exponent is even, so we will keep that sign. Now, our job was to figure out where h double prime is positive for concave up, and that would be everything except 0, because at that point, that's where we found h double prime equaled 0. Or actually, here, h double prime doesn't exist at 0, because it would be the denominator that's 0. Regardless, we can make our conclusion. H of x is concave up on the interval negative infinity to 0 and then 0 to infinity. For our reasoning, we'll say since h double prime of x is greater than 0. So notice I didn't say h double prime of x is concave up because, again, we need to deal with our original function. We want to see where our original function looks like this. And we can figure that out when we analyze the second derivative sign. So let's compare our answers and our work to the grading rubric from the AP. So over here on the right side, you can see the part A was worth a whopping 4 points. 1 point for getting plus or minus 2 for where we had the horizontal tangent line. 1 point for our analysis being making that statement, and then the number line where we're analyzing our extrema. Then we got 2 points for our conclusion, which is that this is the local min, and probably the second point, that this is the local min. Notice you lose 1 point for not putting the 0 onto the number line. Okay, cool, so we got all 4 points there. For B, it's worth 3 points. The first point is for getting the second derivative correct. Notice they have it written like this. If I were to get common denominators, then it would become exactly what we have. So we did get those points. And then you get another point for this analysis, which is part of our explanation. That's why I'm always stressing that you need to explain your reasoning. Then you get 1 point for the answer, which is to say it's concave up for everything except 0. That's the same thing as the interval that we gave for our answer. So hopefully that was helpful. We'll look at C and D in the next video.